to introduce Nancy Songer. She was in the very first cohort of our EMST program. I'm sure she can tell you fascinating stories about how we sometimes had courses arranged by the fourth week of the semester, and we were kind of negotiating what the requirements were, which, but luckily we were flexible about what students did as well. But Nancy was a really marvelous exemplar of the kind of person that we wanted. She came in with a science background and she wanted to do education, and she was very innovative and thoughtful. She took the design course I'm teaching now and built one of the most amazing models using basically, I would say, pixels. It was very, very effective. And then she's had a really good career of doing all sorts of interesting things. She was at the University of Colorado and then at the University of Michigan, where I think she's going to talk about some of the work that she started there. Nancy was one of the leaders in innovating partnerships of scientists and teachers and school districts and researchers to really come up with something that took advantage of all of those elements. And it was at a time when that was really not being done very much. And I was fortunate to be an advisor to one of the committees, and I mean, she had to negotiate with school districts in ways that you just were unbelievable. And then the scientists, they were also like, oh, well, this is private. Well, really? But no, it was really a fascinating, she was really a pioneer in doing this, and many of us now still follow that model that she innovated. And then Nancy went on to become the dean at Drexel, where she was a very innovative leader and revitalized the School of Education there, and has, and now as she's moving to do even more interesting things in a broader scale to try to influence the curriculum practices in schools and universities. So we're really looking forward to hearing what you have to say.
Great, thanks so much. All right, so this is really fun for me. It does feel a little bit like coming home, since I was in that very early cohort of a year not yet identified. It's also just fun to see that the colloquium series still exists. It's still on Monday afternoons, still has some snacks. Some things I think just never change, so it's really fun being back here. I want to thank, these are just some of the people that, you know, this slide isn't nearly big enough, but these were some of my main collaborators for each of the 3 stories and projects that I'm going to talk about. The Detroit-based team, I was there for 18 years at the University of Michigan, and we had projects in Detroit Public Schools for the entire time. So clearly that's not the full list. Cairo is a new project. I'm in my first year, but the project's in its 6th year. I've already been to Cairo twice, and I'm going again later this month. It's a really vibrant project that I'm excited to talk about. And then Philadelphia is a relatively new NSF project that's just in its beginning its 3rd year of funding. So I'm going to talk about what's similar and different across these 3 contexts and programs, and what we can learn by looking both individually at each one and at the big picture across them. So one of the things I was very fortunate to be a part of is about a year and a half ago, I was asked by the National Academies of Sciences, Engineering, and Medicine to chair with Brett Moulding a committee that was looking at how do we enact the vision that's in a framework for K-12 science education. And that vision, and which I'll talk about in a minute, was really doing a complete overhaul of what classroom practice should look like, what activities should look like, what assessment should look like, what pedagogy should look like. And they needed a book that would try to make all of those big kind of visionary ideas in the framework much more practical for everyone to be able to implement. And so this book has just come out. It has a 2019 publication date. And the big idea from the book, which is also in the title, is that research studies tell us that science investigation and engineering design are more effective for supporting learning than traditional teaching methods. And as a result, investigation and design should be the central approach for teaching and learning all science and engineering. So that seems like a really straightforward idea that builds up of empirical research, but as we're going to talk about, and as many of you might know from your own work, making this happen in real classroom settings and getting all the system pieces to work in concert together is a very challenging thing. And so that's what I'm going to talk about in these 3 stories. But my path to science investigations began a long time before that National Academy report. In the summer of 1992, when I was a 7th grader in Menlo Park, Encinal School, the teacher came in at the last day or last week of 7th grade and said, your assignment before the first day of 8th grade is to collect 50 unique species of insects before the first day of 8th grade. Now, that sounds like a crazy, impossible task. At least we all thought it was like, you know, who is this guy? He's crazy. But as it turns out, there's so many species of insects, even with all of the things going on with climate change and other kinds of habitat destruction, that it actually wasn't out of our reach. And so I actually also ended up, for some reason, on the cover of the Palo Alto Times that same summer. This is why that picture's there. Although, you might notice that the caption says, Nancy Butler holds a shell for David Flint to identify. So I only get to hold the shell, and David Flint actually gets to do the science. So again, some gender stuff, you know, hopefully we've made progress since then.
Where is he today?
That's a really good question. I have no idea what happened to David Flint. Okay, so science investigation continues. As we've already talked about, I was one of the earlier Marcia Lynn students. That's me at Sathergate with my then 3-month-old daughter. I fast forward and gave you a picture of her today. She's 29. And then, of course, we worked with these kinds of technologies: Apple IIs, probeware, Mr. K's classroom at Foothill Middle School. It was a fabulous experience, and we definitely were doing science investigations. Again, that have many of the features that we're still working on enacting today. So just to review some of the big ideas that came from that vision document. I know most of you maybe know this if you have done stuff in science, but I'm just putting that here for a refresh. All learning goals in the next generation science standards have 3 dimensions, and those dimensions are science and engineering practices, disciplinary core ideas, and cross-cutting concepts are the big themes. And then ideally they're all blended or integrated or fused or merged into the learning goals. And this is a learning goal here: middle school life science 2, construct an argument supported by empirical evidence that changes to physical or biological components of an ecosystem affect populations. So you can see that this is a pretty ambitious learning goal, and it would require a lot of guidance and scaffolding to get kids to that point. And that's something that, again, investigations and design, curriculum and pedagogy is really helping us to figure out. So the report that I mentioned has several big ideas, and I'm just going to highlight a few here. The first one I already talked about. As a result, investigation and design should be the central approach for all teaching and learning in science and engineering. Another big point, which again might be obvious, but it was helpful that the report really pointed it out very clearly, is that science investigation and engineering design entail a dramatic shift in the classroom dynamic. So it's going to look really different, what kids are doing, what teachers are doing, what assessment looks like, etc. So they give you some examples here. Students ask questions, participate in discussions, create artifacts and models to show their reasoning, and continuously reflect and revise their thinking. Teachers guide, frame, and facilitate the learning environment to allow student engagement and learning. Okay, so again, we all know what those classrooms look like. I'm sure we've seen many of them, but it isn't. If you go, especially globally, but also in the US, this is not the norm in terms of what science and engineering instruction really looks like today. As much as we might know this is what we want to get to, it really isn't happening. Other things that were important in the report is it talks a lot about notable inequities in the system, and I think this is a really important finding that we all need to work with addressing. And I like this report's ideas of giving specific charges to deal with those inequities, like this one here for school administrators. It says that school administrators are asked to gather data on inequities, use these data to make changes and provide additional resources to schools with significant populations of underserved students to broaden access and opportunity for learning through investigation and design. And that's only one of about 5 different strategies that the report gives in order to help us get and deal with these deep-seated inequities. Finally, I also like this kind of a conclusion, which is that teachers are the change agents in guiding, framing, and facilitating investigation and design in classrooms. And I think, again, any of us that have spent time in classrooms know that's true. It's still really important to empower and support teachers as the change agents so that we can get the kinds of practices happening on a regular basis, especially in the cases where whatever the magic is that NSF might have funded goes away. So the report has diagrams like this one, and this is just kind of similar to that second point I just made, where it looks at what normally happens in a traditional science classroom. You have initiate, respond, evaluate kinds of discussions, seat work, textbook labs. We all know this stuff. And that the goal is knowledge of vocabulary, facts, and concepts. In contrast, we're talking about shifting the whole ecosystem so that it's not like you have anything that goes in any particular order, but you want all of these things going on in your classroom at various points and interacting with each other and overlapping, etc. So learning in collaborative groups works with engaging in argument from evidence, for example. Obtaining data and information goes with access to relevant materials and resources and sense-making discussions. I mean, they kind of all, or many of them, touch on each other in order to actually realize those results. So again, it's a different kind of ecosystem, and then the product, of course, is different. Project-based learning to make sense of the natural and engineered world. Okay, so now I'm going to shift to my first of 3 stories. I've given you a little bit of an outline about science investigation and engineering design, and now I'm going to tell you 3 different stories of projects I've worked with over several years, and then we're going to examine whether we think those projects are actually realizing these kind of ideals that we're talking about, especially these kinds of things in this ecosystem circle here, or not, and what we can learn from that examination. I have a little weird cough, so I'm going to have to drink water. Okay, the first story is Detroit. And again, I was faculty at Michigan for 18 years. 13 years I had concentrated in this project with my very wonderful co-principal investigator, Phil Myers, who's a professor of zoology. So Marcia talked about partnerships. I can't say enough about how fabulous the partnerships I've had with scientists were. And they take, like any partnership, a tremendous amount of effort and nurturing and even just like deep, difficult conversations so that we could all understand each other's worlds. Like we had a lot of those where some of the postdocs in zoology would say, well, we don't understand what you mean by scaffolding, or like, you know, that's not the right example because they did know. But there were lots of questions about our very sort of somewhat vague education terms. And I felt like it was such a productive exercise, actually, for us to have to try to break those terms down, help them manifest them, and then really have the postdocs in zoology be co-developers of all of our educational materials. And that way the science quality was of utmost integrity, and the kids were really doing more of the thinking like scientists, but in a more simplified, we'll tell you in a minute, we call it strategic simplification, like a strategically simplified manner. They were doing much of the thinking that actually the scientists had told us was common in their professional discussions. So this is a Education Week story on our project, and I like the headline, that's why I put it in there, Scientific Reasoning, No Child's Play. So this was 5th graders that were running around in the schoolyard collecting bugs and actually making a lot of critical thinking decisions and explanations with their own data. So some program features of the Detroit project. It was always an 8-week curriculum that focused on one major investigation. In this particular case, it was gathering data on all the animals in their schoolyard, entering it into this mobile app that I'll tell you about, and then looking at their own data to try to determine and be able to justify which schoolyard area was the most biodiverse and why. What kinds of evidence could they draw on from their own data to make a claim for how biodiverse the schoolyard was or wasn't. There were at least 10 opportunities within the curricular binder for every student to construct guided or fated claims and evidence. This is a claim and evidence guided activity. This was actually a claim, evidence, and reasoning, or in other words, that was called explanation in those days. This one has more scaffolding. You can see this is like, you know, fill in the sentences. It's like the very first claim evidence thing we did where we gave them sentence starters. And then we have these hints. compare the number of animals in each animal group by looking at the bars of your graph. So early on, we give them a lot of hints to try to guide them into doing this construction of explanations. Later on, we take away a lot of those hints, like what the definition of a claim and evidence is, so that they can then be doing that on their own, so that by the time they get to this on an open-ended constructed response item, they're actually very comfortable with that kind of stuff. All the data they used was student-generated using mobile apps modeled after a professional tool, and it was customized for the NSF project. And all assessment prioritized 3D learning goals. Again, our assessment questions look more like these, not like any kind of multiple choice thing, which made coding more challenging, but that's the way it was. Okay, you all know that probably too. We developed some pretty cool apps and other resources. Phil Myers had a species database with thousands of animal species accounts in there called Animal Diversity Web. We rewrote that into something called Critter Catalog. So we had a species account for every animal they might see in the schoolyard that gave them like what it ate it, what it looked like, what its habitat was. So kids could do more accurate identification and more food web kinds of activities using the stuff that they collected. That's now become a much more successful app. Actually, we have a new grant pending with NSF that's going to be taking this to a whole bunch of communities worldwide. This is what the app ended up look like in, I think, its best form. It has a series of screens. This is modeled after a tool called CyberTracker that is used by professional animal trackers in Africa. And we got permission to rewrite the code for Detroit animals and kids. And then our zoologists, of course, put all the right Detroit animals into our database as opposed to things like zebra, right? Or hippos. I don't even know what they're so anyway, they go through and see what it is that they're sensing, what do you sense, what animal group is it in, what type of we picked reptile, then what kind of reptile is it, where is it located, what's it doing, notes. And then this is a final list that will tally all of the sightings that you did in one observation, field observation experience. Then all their data is uploaded to these databases, and now you can see that everything that Zone A collected is that first column. And they got, they saw 2 earthworms, 2 ants, an invert, and some mourning doves, etc. So then the data are all organized so that you get to use, your data has value because you were part of Zone A, but everybody's data has value because you need everybody in the class's data in order to be able to make that explanation later about which zone of the schoolyard has the greatest biodiversity. So everybody's knowledge is important. That's another feature we'll talk about later. We hired an artist to create some comics. We wanted to make the learning have a variety of different learning modes and preferences for different kinds of learning styles. This is one about an invasive species in the Detroit River ecosystem. And again, like, I don't know, this stuff is really fun, really, I don't know. I like these parts of it to like really think in more creative ways about how you make the learning engaging in a lot of different learning modes. And then eventually, all of our explanation construction was online with these rollover hints. Again, like definitions of what evidence is, definition of reasoning and claims. And you could choose not to have those be here. And then these were the content hints that, again, could be accessed or not. This made the scaffold and fade go much more easily and more controllable by the teacher, which is also something that was important because we wanted to have more guidance early on, and then we wanted to fade it later on in the 8-week curriculum. So learning results were good. This is our kind of very early stuff where we were looking at how kids in Michigan did on state tests, which is called the NEAP at 8th grade, how Detroit public school kids did, and then how our kids in schools that we had worked with for 1 to 4 of our 8-week curricular units, how they did. And you can see that there's some these are reasonably substantively good gains, considering, again, how difficult it is to show the kind of learning that we were doing represented well in a standardized test. Again, there's a complete mismatch in terms of what the standardized test was actually measuring, and yet we still had very significant gains from kids in our classes. This is a more detailed kind of result, and I'm just going to explain it kind of briefly because I think it's it's sometimes you have to do different kinds of analyses in order to be able to show impact of something. So what happened was we had about 1,800 kids in 22 different 6th grade classes. It was all the 6th grade classes in Detroit at that time. And we got permission to work and do professional development with every teacher in Detroit 6th grade. And then the teacher got to pick whether they wanted to do our 8-week program for ecology or whether they wanted to do the district-issued textbook. And then we looked at how much of the textbook or how much of our, this is how much of our stuff they used, okay? So if they did all 8 weeks of our stuff, they would be down here in 100% intervention. If they did 0 of our stuff, they'd be down here in 1 to 10%, because this is all textbook, okay? So this is a dose-response study, and we did this because we wanted to give each teacher the ability to have the freedom to use as much of our stuff as they wanted and they were comfortable with. And then we wanted to see what was the effect of using our kind of program that had a lot of these constructed explanation activities that were more labor-intensive and more cognitively challenging. What was the outcome of that based on the amount of intervention that the class had had? So the overall results were then measured by both release standardized test items, which were multiple choice, kind of factual, and then these complex items are where they have to construct an explanation to answer a question, like the ones you saw before. So if you look at the standardized items, you can see that even the kids that use the textbook have a significant learning gain. This is a significant gain pre-post on using the standardized items, but if you look at the slope of that, our kids are significantly better than these kids, even on the standardized multiple choice items that were not at all how they learned learned ecology. But the more important conclusion is that the kids who had the textbook did pretty dismal on anything where they had to construct a response item, and our kids were like flippantly great, right? So, I mean, it was really, we had like 0.67 effect size, like it's a huge learning difference as a result of our kids being very comfortable with that scaffold and fade activity format that they had had over several weeks. Okay, that's story 1. Story 2 is Cairo.
Do you have time for a question for you?
Yeah, please.
So maybe this was a point of concern over a while, but you gravitated to an answer. But the fundamental question of like which yard is more biodiverse.
Yeah.
What if you had lots of critters in one group,
Yeah.
but another yard had lots of groups but not as many critters?
Yeah.
Was there like a hierarchical notion, or
Yeah.
did you just count up all the critters?
No, so I'm so glad you asked that, because that's exactly the definition of biodiversity that we got from the scientists was you have to take species abundance and species richness into account. So abundance is total count of animals that you saw. Richness is the number of different unique species. So we had to train middle school kids to be looking at both abundance and richness, just like you're saying, but it's not summative. Like you can't just like add up abundance plus richness and then say that one's more biodiverse, because that's not an accurate, scientifically accurate simplification of what the term biodiversity means. So we had these very sort of complex discussions. It's that meaning-making discussion circle that was in previously about, again, like why is it you can't just count, and what does it mean to have lots of different kinds of animals, and it turns out they had discussions about, well, that's probably better, like if you have uncertainty, like one has like slightly more higher number, but has a much lower number of different kinds, that's probably not as biodiverse as the one that has more different kinds of animals. That's a better biodiversity, like a better web. So we talked about, like, again, like many more species makes for a more stable web. So I guess the story that I'm trying to explain is that there's lots of things that go into, again, this process of what we call strategic simplification, where you're trying to get at very sophisticated thinking, but in an age-appropriate way that still maintains some of the richness and complexity of the domain that you want to keep to make it engaging for kids, and also so they're really learning some actual science. And getting that to a middle school audience is really not always easy or straightforward, but having scientists on our team to help us say, oh yeah, this is how we think about biodiversity, and this is why you can't, like of course we could have figured out you can't just add, it's not just summative, but it was so helpful to have their thinking process to guide that kind of conversation.
I saw richness on the slide,
yeah,
and I was wondering, was that's good to know?
Yeah, that's what it means, so again. So I know even with Marcia, when I was a grad student, we were talking about heat energy and how you get a simple but sophisticated definition of that term that kids can manage and reason with that's not scientifically incorrect. And I know some physicists were grumbling because it wasn't quite right, right, Marcia?
Oh, they were furious.
Yeah, that's right. That's what I remember
Then we
too.
got really hysterically funny physicists to write that this was absolutely the right way to go. And then everybody kind of shut up.
Yeah, you need. I think that's right though. If you have a legitimate scientist that backs your perspective, then it's okay.
Right.
Yeah.
You had like potatoes and wool versus aluminum or things like that, if I recall, right?
That is what we had.
We had a heat flow model, which it turns out engineers use all the time. And so once the engineers chimed in and said, no, we want students to learn this model, then it was okay.
Yeah.
Like,
It's too bad that us, science educators aren't legitimate.
Are so valuable.
Yeah.
I mean,
No, the partnership actually was huge. Okay. Any other questions before we switch to Cairo? Okay, so Cairo is $25 5-year grants, 2 rounds now. We just started the 2nd round. And the goal is to have one interdisciplinary STEM high school, and their high school is only 3 years, in every governorate of Egypt. So there's 27 geographic regions within Egypt. They're called governances, something like that. And excuse me, this is such the program takes high-achieving high school kids, and they come to these high schools, and they're boarding high schools, and they live there for 3 years, and they do these very complicated capstone interdisciplinary projects that integrate physics and chemistry and biology and earth science. So the high school curriculum was designed 6 years ago, and it was designed around Egypt's 10 grand challenges. Things like reduce urban congestion, deal with exponential population growth, reduce pollution, recycle and retain garbage, work to eradicate public health issues and disease. And I think it's so cool that they picked this as the backbone and investigation and design focus for the entire 3-year curriculum. So they take English, they take Arabic, they actually learn all their STEM classes in English, even though of course their native regular language is Arabic, because they want the students to be globally competitive in the world, and so that's why the STEM classes are in English. But it's a huge challenge, obviously, to not only have all the materials and all the projects be in English, but to have all the teachers, the high school teachers, be teaching STEM in English. That's just another one of the problems. Okay. They have these guiding principles. You might recognize them. Some of the great, STEM schools in the States have very similar ones. They want to promote thinking independently, creatively, and analytically, preparing students to be scientifically, mathematically, and technologically literate and proficient, promoting an environment of questioning, collaboration, and high level of communication, value and promote self-motivation, self-direction, and lifelong learning. These are very bold goals. And this top one in bold here is actually probably the, like the foundational idea for the whole STEM high school, which is that each semester culminates in an interdisciplinary capstone project using investigation and engineering design to solve one of Egypt's grand challenges. So they say something like, in your sophomore year, energy, second semester energy is the big theme. And so you have to design a capstone project with 2 or 3 other students that will solve something about Egypt's problems with energy for future generations, okay? They also have as a goal to ensure all graduating students will be admitted and competitive to a university, and they are actually, many of them are going not just to Egyptian universities but all over the world, and then foster the development of socially responsible leaders with a consciousness and eye towards a more contemporary Egypt, solving the future while addressing the largest grand challenges. So I have just one sample project here, UV-free lamps for a healthier life, and you can't obviously read this, but I think what I'm just trying to illustrate is that if you were able to read this text, I determined that this was about on par with like a master's level, a senior undergraduate or master's level thesis in terms of its complexity, its scientific complexity. And that is also evident because they go to the universities. The high school kids go to the universities and use many of the apparatus that are being used by engineers and physicists and chemists and stuff at the university in order to be able to both create products in the fab lab and run their experiments that they need to solve these ideas for the grand challenges. So anyway, it's quite detailed set of activities. And now I'm going to show you a short video from them. One minute or so, 1.5. The sound, it's mostly music. Pretty soft. Well, when she talks, you might not be able to hear her back.
I came here because actually I'm good memorizing, but I do not think that memorizing would help me in things. I wanted to actually think outside the box and many things, facing problems, and the social and skills I gained here, I felt I would gain here, would actually the valid reason for me to come.
That's an Intel, again, international Intel competition with like huge,
بس احنا
huge
اشتغلنا
deal.
كل يوم كنا بنسهر على البروجكت ده كنا عايزين فعلا نحقق حاجه لمصر كنا متخيلين احنا عارفين ان مصر هتتبني بينا وربنا حقق لنا حلمنا ويا رب نوصل للنهائي ونشرف مصر ومصر تتبني بينا ان شاء الله. بحب اشكر المدرسه بتاعتنا اللي هي اللي اتبنت المشروع ده وهي اللي قعدت تصرف علينا وهي اللي قعدت تشجعنا ويوم ورا التاني وانتوا هتقدروا وانتوا هتقدروا تبنوا وتعملوا.
Okay, so again, this is just like such a cool project. I feel really, really excited that I get to participate with it, be part of it. It's a really big team, but okay. So in the 7 years since the first STEM school was opened, they've established this untraditional educational model based on the grand challenges. This is like a seismic shift compared to the curriculum in the other Egyptian high schools. It's really, really, this all project-based capstone stuff is really different. 14 fully operated STEM schools with more than 1,800 students, students participating in national science competitions, and more than 96% of student graduates are studying in higher ranking universities in Egypt, US, and other countries. And they're doing very well. These are the ones that won the award in the article that was on that. Okay, any questions about Egypt before we... I don't have learning results because I had very recently joined the project, so I can only show you what others have put together. Yeah?
Who set the grand challenges for Egypt? Where did those come from?
It came from somewhere in the... So the Ministry of Education... it's somewhere in the government structure. I don't actually know because I wasn't on the project at that time, but they were looking for a model of how to organize the STEM curriculum, and that was one of, it was already part of, part of their, some of their government policy documents already. It obviously wasn't a school curriculum yet. Yeah?
What's your role in the project?
So my role is that in the second 5-year grant, which started about 6 months ago, I'm leading a team that is working with Egyptian faculty to develop the teacher education program that will train teachers to be able to teach in these multidisciplinary STEM high schools in exemplary kinds of way. Again, promoting the same kinds of pedagogical ideas and classroom practice changes that we've been talking about already. Okay. Right. All right, story 3. This is Philadelphia. It's the newest project. Only $2 million funding so far. It's off to a good start, but again, it's only been going since 2016. Program features are, it's a younger audience. So for the first time, we're actually looking at kind of late elementary, early, middle, or one of the first times. We're also working with kids that are both in school, informal classrooms, and out of school clubs. We wanted to see if we could try to do this project-based activities and reach a variety of different students. It's only a 4-week curriculum. The grain is smaller, and the work, we wanted to be reasonable about what we could develop in the amount of time that we had. So we have, in 4 weeks, we have 5 of these opportunities where they construct and practice constructing claim evidence and reasoning or other kinds of 3-dimensional learning goals. We have created a new mobile app, and all the data, once again, is student generated. Once again, all the assessment prioritized 3D learning goals, not like multiple choice. And the one difference here is every student group uses the engineering design process to generate a local solution that builds off of their own data collection to generate a solution. So in the beginning, students are invited to become animal trackers. This is actually a real animal tracker that I met in Uganda. He is an expert on mountain gorillas. And so I actually went on an animal tracking expedition with this gentleman. And we had him help us draft a letter of invitation to our Philadelphia students to invite them to be animal trackers and track information and animals in their own neighborhoods. So we, again, have a mobile app that records all the animal sightings that they have. We use this quite simplified local ecosystem as our model of the kinds of things that they might expect to see, and then what eats what, so that they can talk later. Later on, they have to look at what they have observed, they have to see what they didn't observe, and then they have to decide what they might introduce or what kind of change they could introduce to Philadelphia neighborhoods in order to potentially increase the strength of the food web and the biodiversity of their local urban neighborhood. So again, it's trying to find this purpose, this larger purpose for their own data collection and their own science learning. So the Capstone, the final project, mirrors simple solutions used by professionals to increase urban biodiversity. We looked at what scientists were doing. It turns out right before the 2012 London Olympics, some scientists introduced some native wildflowers near some of the Olympic grounds, and they ended up getting all these pollinating insects that they hadn't previously understood, were even maybe possible to be there, and they were all excited. So these kinds of relatively simple changes that actually can sometimes make some relatively profound differences in the variety of organisms that you might have in urban areas. And as the world gets even more urban, I think this kind of study is actually a really interesting thing for kids to be a part of. So students use their school data and that Philly food web to determine a change or solution that would increase local biodiversity. And then the unit ends with the solution design presentations to community leaders. Here's a group that just did their presentations in December, and their teacher. They were actually super good. We have badges now. Kids and teachers get badges. This is just showing the sequence of badges that they would get throughout the curriculum. And we have very early learning results, and I'm kind of a little embarrassed to put these up here because we haven't done very sophisticated statistics yet, but we're showing that the pre-post gains on every item except like 1 or 2 are significant. And so now we're just beginning to sort of unpack and look more carefully at, even in a 4-week unit, what kinds of demonstrations of learning in these more complex kinds of items kids can generate. All right, so what do these 3 stories have in common? Now I'm going to shift to what is my current thinking. I'm actually writing a paper that's sort of summarizing all of this, and I came up with 7 S's, 7 things that start with S, that I think are central to these 3 cases and central to the projects that I've done in terms of realizing this success with investigation and engineering design. And that's how I'm going to walk you through them, okay? You might notice that the number doesn't actually reach 7. That's fair. Okay. So number 1, I believe that to realize systemic change, all materials, assessment, professional development, and instruction is focused around what I'm calling a spine, a particular investigation or design challenge that's the backbone and anchor for all of these materials. So they have to all be coordinated, they have to all be developed, and it has to be a really rich local phenomenon investigation or engineering design problem, just like it was in Egypt, just like it was in Detroit, and just like it was in Philadelphia. So kids find value in learning about that. So as I've already mentioned, the spine in Egypt was really clear. The grand challenges was a real obvious thing that kids could rally around. They said things like, you know, we're solving Egypt's problems. I think there was something like that in that quote. And they take ownership for their learning because they see that their learning has value. So that spine is really important. Any questions about the spine? Okay, I'll just keep going through. All right, number 2. This is a little wonky, but lessons must be organized in a sequence that builds coherence and three-dimensional learning over lessons, units, and years, okay? So you don't want it to be super constricted, but it has to have some systematic building so that you can have both scaffolds and fades over time. This is one of our units. It has 10 lessons over 8 weeks, and these are the science and engineering practices on this axis. So what they do is they collect data. Again, like let's say they go out into the schoolyard. It wasn't what this one was, so that's okay. Go out in the schoolyard and collect data. Then they analyze that data. Then they make an explanation from that set of data. Then they actually go back and analyze different parts of the data, and then they do another explanation. And then they analyze again, and they do another explanation. So all of this actually, this is like an oscillating pattern of using your data and doing analysis and then reaching conclusions or results, explanation, and then go back and rethinking. That has proven to be a really powerful sequence of activities. And so we've repeated it now in several of our units. We have data, and then you have this oscillation. You have another new set of data, new oscillations, and then a third set of data in this particular unit, and some oscillations, okay? These stars were these capstone activities which we used as a formative assessment time to really gather more data on what was and wasn't working and to try to see if our instructional practices needed some adjustments or tweaks in the middle, and then towards the end it was a summative one. So, okay, so that's S sequence. All right. S3, classroom practices are different in these kinds of environments. We've seen that many times. Learning has to be reasonably challenging with the ability to manage appropriate struggle with guidance as needed. Okay, so I go back to my 7th grade self where I was given that 50 species of unique insects. That was an appropriate struggle, but I had guidance, and there was something very, very enticing about stretching my abilities slightly beyond what I thought I could do on my own, right? So very much zone or proximal development kind of ideas where you're doing things that are maybe just outside of what your reach, what you might be able to do on your own, but it makes for a more deeply engaging learning experience than I might have otherwise done on my own. So the kinds of struggle and guidance we have to think about is, what does classroom talk sound like in these sense-making discussions? How is practice different? How are alternative conceptions different? Your goal is higher, your learning goals are higher. So your misconceptions or alternative conceptions are also going to be different than if you were just memorizing or coming up with more simple kinds of definitions. How are ideas like evidence scaffolded, discussed, and revisited? All right. Students practice and learn to use collaboration, multiple expertise, and synergy in order to address challenging questions. Okay, so this is just working in teams, building consensus and/or products that represent multiple different students' views and expertise and ideas in a comprehensive way. So if you've ever guided middle school or high school kids in groups, this is obviously no easy task, right? There's a lot of things going on about social dynamics. It's much harder to realize actually than most people think. But anyway, obviously it's really important. You're not going to get to those end products if you don't have a good plan for how people work together. Number 5. Products of learning need to be important. They need to have a purpose or substance and/or an audience of supporters. So these are the Detroit kids. The last thing they did in Detroit was we put them all on buses. We brought them to the University of Michigan. We set up their poster boards in this big auditorium at Michigan. And they were the experts on the Detroit River ecosystem animals that they had studied. And then we had faculty and graduate students in the life sciences come around and ask them questions about their posters. So this made their learning valuable for others, and it was our first attempt, which I think we've gotten a little better at actually, but obviously these people were quite engaged. But you know, you want to have learning have value, and you want to have an audience of supporters, or somebody who's going to recognize that your learning has value. So I think Egypt is a really good example of that learning having value. Again, the grand challenges, we are solving Egypt's problems. Kids really know why they're learning these things. It's not just to, like, you know, fill out a test or because their teacher says they have to. Like the other ones in Philly, scientists, they also have engineering design where they present to community leaders. Okay, S6. We want to gather evidence of learning steps, not only endpoints. So this is just the embedded formative assessment argument that when you're trying to guide a more complex kind of learning, you can't just only look at endpoints. You have to look at progress. You have to look at where learning falters so you can make tweaks and adjustments. And you have to really know more about, again, like where things might go wrong in a way that if you were doing a more straightforward kind of lesson or textbook reading, it really isn't quite as necessary because there's more places to go wrong and it's more complicated. So this book that I was part of this committee, this is another National Academy of Science book on how you assess next generation science standards. Basically, these ideas are still really true. Measure progress and gather evidence of where 3D learning stumbles. Multiple choice items really cannot provide strong evidence of investigation and design and the learning that happens in those. So it's not like they have no place, but you just want to minimalize how much information you expect to be drawing from those. And then this is something that's in this book that I think is actually not always talked about. You can do test questions in bundles. So again, like a lot of more sophisticated standardized tests do this now, where you have like a picture or a stem or a chart, and then you have a multiple choice that maybe just asks them to read the chart. That's okay, because that's useful information just to see if they know where to go in the chart to get the right information. And then, so that's the first item in the bundle. And then you have like 2 or 3 more that might be more constructive response, complex kinds of things, where they have to make analysis or they have to design an explanation. And that way you can actually get a lot of information from those 3 questions and around that one bundle than you might if you had to have every single question have its own scenario or data set in order to, you know, to get for the test, okay? So it's also kind of an efficiency thing. All right. S7, partnerships, funding, and learning must be sustained over years or even decades. I think this is the maybe the most important one. And our systems of schools and universities and funding, they don't really work under this model. Like, the students' learning has to be sustained over several weeks or months, or you will not get them to develop that deep understanding of these complex learning goals that we put up early on in a short period of time. It just isn't possible. There's too much guidance and work that has to be talked about and, you know, sense making that has to go on. Teachers' learning also doesn't happen right away. So we are asking in the report that administrators provide professional learning opportunities over multiple years for teachers so that they can also learn how to do this themselves as well as guide it in others. It's really important in making it happen. And then NSF grants tend to be 3 years now, and I had 2 grants that were 5 years. I cannot tell you what an enormous difference a 5-year grant can make on what you can accomplish, because you already have all the partnerships in place. You have the software there, you have the curriculum, the teachers are doing the professional development, and what you can realize in the last 2 years is just like 4 times as much as what you were able to do in the first 3. So again, we don't have the funding models, but I think it's just good for us to be reminded that whenever possible, we want to be in this for the long haul to get the kind of change that we desire. Any questions about that? All right. I'm going to come back to this. So I have these 7, and then I added 8 today. So like it's kind of messed up my numbering system. But I realized as I was going through all this work that this strategic simplification idea of both scientific ideas and the technologies is really important, because you want the kids to be doing work that's using professional-like tools and thinking that's professional in many dimensions, but obviously not exactly like how professionals do it. And so that process of which pieces you simplify, how you redesign the interface of the tool, like for the data collection tool that's on the mobile app. How do we simplify it in a way that kids are going to not only be able to use it fluidly, but then draw on their information in productive ways to get to that explanation, construction, or the solution? That's a lot of thinking, a lot of complex kind of unpacking of complex terms. and technologies to get to that point. So I actually almost think that this one is one of my most important, and so I'm really happy that I'm giving this talk because it's helping me to really reformulate the talk in important ways. Okay, so I'm just going to walk through strategic simplification really quickly, what we've done with it. I like this quote from Steve Jobs because it's, you know, he says a lot of good things and whatever, but simple can be harder than complex. You have to work hard to get your thinking cleaned and make it simple, but it's worth it in the end because once you get there, you can move mountains. And of course, Apple really was so good at getting things simplified. But I think getting a technology simple is so hard, but really, really important. So anyway, way back when, I worked with an atmospheric scientist, and we did this tool that had kids forecasting live hurricanes off the eastern coast. It was like the coolest thing. And we had these like vectors where you could this blue dots is every 6 hours where the actual hurricane went, and then you could slide the slider bar, and you could say like in 24 hours, if it's going at the same speed in the same direction, where will the hurricane hit? And the kids were like making predictions about which city should be under hurricane watch or hurricane warning. It was like so fun. So anyway, that was taking all of this very complicated science and putting it into a tool that was very powerful, I think, for kids' use. Then this one I've already talked about. This was another one we did where we took it's called predictive distribution modeling, where you look at where animals can live now. That's this hash. And then we took Intergovernmental Panel on Climate Change scenarios of what is going to happen under various different clean energy and population scenarios in the year 2100. Okay, and under some scenarios, this animal, the red squirrel, is going to be moving dramatically north in order to be able to find its prey and also to find the right microhabitat and climate for it to survive. So the whole reason why we did this whole tool was we were trying to help kids understand impacts of climate change in a way that was more tangible than just like 1 or 2 degrees Celsius, hotter. And we found that this tool was actually a really interesting thing. But there was a really pretty dramatic process of strategic simplification to get that tool to be usable by middle and high school kids. Okay, so now in conclusion, these were the original 7, and I went through and tried to say, in the 3 scenarios, where do we see those things, okay? So number 1, the spine. Did we see the spine in Detroit? Yes, absolutely. They had that investigation of collecting the data, and then they had to say which zone of the schoolyard was the most biodiverse. Cairo, definitely they had a spine. Philadelphia, I think the spine is a little weak, in part because, so I only gave it a check, because it's only 4 weeks, and I think there is a really good investigation there, but there isn't quite enough heft to it for them to really focus some deeper learning. So I am sort of thinking that we're slightly under realizing what we might want to do for a spine in Philadelphia at the present time. Sequence. Do we have a sequence? Yes, again, in Detroit and in Cairo, they have very clear mapped out sequences of activities that end in capstones. We also have it in Philadelphia, but it's the same kind of problem. It's just too short, I think, for the kind of deeper learning, especially with slightly younger kids. You can't get to the more sophisticated things in a way I really feel comfortable. Appropriate struggle, all 3 of them I think did a good job on that. Synergy, yes, we worked really carefully in all these cases in guiding kids in roles and various kinds of ways to work productively together. Number 5, the learning has substance and supporters. Absolutely. In the first 2, and actually Philadelphia is pretty good, but again, maybe just because the solutions aren't fully realized, I think this, like the shortness of the curriculum is sort of impacting several of these different dimensions in a way that's, it's okay, it just could be a little bit better. Evidence of learning steps, we definitely have designed our own assessment in every case so that we have good evidence of progress and critical thinking at various time points along the way. And what does the sustainability package look like? Well, here again, it was like 11 years. It was actually more like 13. And this one has a promise of 10 because the funding is in place. And this one, it's a check because we only have the first grant and we only have 3 years. But again, it's making good progress. So in sum, I feel like these first 2 examples have done a really excellent job of realizing these 7 necessary components of the investigation and engineering design success. And the Philadelphia one is pretty good, but it's not really all there yet. I think it needs some work, and mostly because the combination of the kids being younger and the curriculum being shorter means we aren't really able to sort of do the deeper investment that we care the most about. Oh, okay, so in conclusion, I think all 8 S's are essential for systemic change with investigation and design. Perhaps the most understudied is the last one I added, because I think there's a lot of knowledge going on there that I'm actually working on a different paper on to really codify, but it's a really rich topic that I would love any of your dialogue about. I think the most difficult to realize is S7, sustained partnerships, funding, and learning, as we've already talked about. In particular, grant funding cycles are limited, people move, etc., have lives. It's difficult to moderate expectations of systemic change, so everyone wants the change to happen like yesterday, and they don't understand that it just, sometimes it's like 2 or 3 years before you really see clean learning results, because you're changing so many pieces of the system, and that's really complicated. And it's also difficult for all partners to provide the time and energy investment involved in decade-long partnerships. So that one, I think, is the most challenging. All right, thank you very much. Any other questions? Yeah. Okay.
I'm sorry to admit that by the end I forgot what the Ds were in the 3D, like what the dimensions were.
Yeah. Okay. So that's the way the knowledge is organized in next generation science standards. And I had a picture that I realized very, very far back. Oh, there it is. Okay, so and Common Core Math has this too. So this is one dimension, this is the second, this is the third. This is the big themes, this is the kind of content core, and both of these sometimes together are called the science content. And then this is the like asking questions, formulating explanations, engaging in argument from evidence. It's like the things you do, to realize understanding of these things. Okay? Yeah. Any other questions? Yeah.
Within the projects that the kids are doing, is there much choice for the students in determining the direction that they want to take their investigation?
So, the Detroit project really didn't provide a lot of choice, but we've changed that in the other two. So, absolutely in Cairo, they have a big theme, but they can do anything they want in that theme. And then in Philadelphia, they get to create their own solutions. So we give them the food web, we give them a modeled solution that they can walk through and talk about, like what this other kid hypothetically did. So, but they can do whatever they want for their solution. And it's kind of cute, they do lots of very different things. And I think that's good. So again, I think we've learned that choice helps with that personal connection piece a lot, and it's really important.
So you kind of have to start with something that you have the expertise around,
right?
But then you want to leave room in there for students to.
Well, that's right. So it's choice within some reasonable constraints. Like they can't do a solution to some other problem. We have sort of constrained what the problem is. That we want their solution to deal with, how to increase biodiversity in Philadelphia. But we're not saying that their solution is going to, like solve pollution problems. So there's choice within reason, but again, I don't know how to guide it effectively, especially with younger kids, if there isn't some constraint. But I think that's always a tension you play with.
Right. But we want to be building in that kind of choice within the standards more.
Absolutely. And again, the report talks about local phenomenon, and so it'll be meaningful and relevant for kids' lives and culture, and that's going to obviously provide tremendously higher motivation than something that's weird and they have no connection to. Great, thank you. Yeah.
So I'm really kind of interested in, you talked a little bit about professional learning for the teachers.
Yeah.
And you were talking a little bit about maybe kind of figuring out ways to better do that, or how do we train teachers to engage in this kind of. Have you done a lot of that, and have you found anything that's particularly difficult, or common challenges or strategies?
We have done a fair amount, and so what I've done the most is since I was on that assessment team, I was hired by the state of Delaware, which is right near me, to do a year and a half of workshops for all of their, Delaware's a small state, but all of their science teacher leaders across K through 12 on how to assess next generation science standards. So this was like so fun actually, because they basically said, you can kind of ask them to do anything you want. And so what we did is we organized this very systemic plan where they, first of all, we introduced it over the summer over a week-long thing. Like what the approach was, gave them some guidance. They had time within their grade level teams to think about the units they were going to be teaching in the fall, and then what kinds of assessments they might design as teams that would get at that learning goal in a better way, more like construction of explanations or other kinds of constructed response items. And then they, between the fall and later in the fall, they ran these units because they knew which sequence of units they were going to run at what time. So they built the assessments for the first couple of units that were running in the fall. They ran the units, they brought the products that kids generated back to the next workshop, and we all looked at them and we're like, oh, that question didn't work right because look, the kids misunderstood, or here's a new kind of, again, alternative conception or misconception that we didn't know, that they don't have any idea what evidence is, or they don't know how to go back to this data source and find the right or relevant information. So I'm going to have to adjust my instruction to do that better. So it was just so productive because it was like this ongoing conversation that had used their actual enactments and then the products of their enactment and discussions with each other about what was working or what wasn't working in different classrooms. And then by the end of the year and a half, they were just like superstars. I mean, they were designing all these really great items, and they were giving all their items to the state people that were designing the Delaware state test for NGSS at the state level. And it was just exactly how I think anybody would want it to be. It was just a really productive experience. So we're going to look at those kinds of things, like how you use professional learning for multiple conversations that can build deeper understanding over time. And I think that's why I put that quote up there from the report about sustained professional learning opportunities. Like we all hope or something, I don't know if we even think this, that we'll just give them a Saturday workshop or a 2-hour after school, and then they'll be ready to do my really super complicated unit, right? It just, we all know that really doesn't work very well.
Did your teachers interact a lot with the scientists too? That Phil Myers and the...
Yes,
they have that
yes. And we
as well?
had our postdocs come out to the schools and lead the professional development workshops.
Okay.
So this one guy, George Hammond, he was an entomologist, so he was the bug guy. So he came out and helped all of the slightly squirmy teachers find bugs, identify bugs, be experts on bugs. It was just so cool. It was really a very, very great partnership. I just wrote a grant with some of them for next round too, so hopefully that will continue. Yeah.
I thought you were going to talk about Cairo in the U.S., not Cairo in Egypt. So.
Oh.
No. But I guess one of the questions I have from the international perspective, and this may require you to speculate or push your expertise, but how do you think the U.S. is doing with respect to these, the standards or the particular way that you'd like to see science in the schoolyard? I mean, are we doing better than we did 20 years ago, but the rest of the world is doing even more better than we are, and so we're falling behind, or there's pockets where there are innovative programs, but kind of not so much elsewhere?
I think pockets is the closest answer, the easiest answer. So I think what's interesting about Egypt and their motivation was they were coming at a deficit. Like they had never sent a high school kid to one of these Intel or other international competitions. And suddenly they were not only going to these things, and they were winning. And it was just like it blew their mind, So, but also the Ministry of Education came on right away, and they have a national curriculum. So if he or she says this is how it's going to be, it's that way in every high school. So they have conveniences, and other countries obviously have this too. They have conveniences like national curriculum that don't get challenged in state, legislatures and all that kind of stuff, that make change go more rapidly. Like I'm actually just like hugely impressed with how rapid the Egypt schools have not only implemented this curriculum, but like trained their early teachers and then running the curriculum, and kids are going off to like much more competitive universities and are winning Intel. Like that's all happened within like 6 years. That's ridiculous. That's like ridiculously fast. So yeah, so that's why it's now become adopted that the Ministry of Education said we don't want it just in certain parts of Egypt. We want every single regional area to have at least one of these magnet high schools. Yeah.
Just how do kids get into that high school? Do they apply? Like, so they're already presumably doing well in science and math in order to get into that.
So they made the decision that you have to be in the top 10% on a standardized test. I don't even know much about this test that they give you in like 8th grade. Okay, but then anybody can apply and anybody can go, and you can go to any region of Egypt. Like you don't have to go to the one that's in your geographic region. So it's somewhat restricted, at least at the present time, because they want it to be sort of more, slightly more advanced students, but otherwise it's anyone who wants to and can go. And the fees are very, very minimal. There's minor fees, but they're not fees that are outrageous for the lifestyle of the average Egyptian, which is really, really important, obviously. You don't want it to be just an elite program. Yeah?
I guess I'm curious because, Egypt has gone through a lot of tumult the past few years, and, some would think that it's kind of been a dictatorial regime. But looking at the 8 different goals, they seemed reasonably benign to me.
Yeah.
But I'm wondering, were there any elements in which politics or some implicit censorship took place in terms of like, one of the goals is no longer in vogue, or...
No, they don't have those kind of political problems. So again, they are seeing the statistics that say countries that adopt higher quality STEM educational programs, especially in either high school or early undergraduate, their gross national product goes up. So this is the way for the country to do better economically. And again, I did another short study actually in Turkmenistan, which had a very traditional educational system, but it was remarkably similar in this particular way, where the Ministry of Education said, we want to strengthen STEM. We've got the 3rd highest natural gas reserves in the country, in the world, and we have nobody or very few people that want to go into STEM fields, especially women. And so we want you to come and talk about STEM education in high school and undergraduate, so more of our kids, and problem-based learning, so more of our kids will see both the value of STEM, but also be more inclined maybe to go on to university and eventually have jobs.
So you did see an interaction with the alternative energies that, by virtue of all this fossil fuel and the gas, that it inhibited solar, wind sort of discussions? Or?
They don't have, as far as I am aware, and I've only been there twice now, but I haven't heard no conversation that had any clash or tension around these topics. Yeah. Yeah.
So I'm curious, now that you've had a chance to think about all these things, and must be fabulously stimulating principles, what should we be thinking about with regard to revamping our graduate programs in STEM and in general, preparing people to be more effective in this? So what do you wish you'd learned? What should we be teaching students?
Like in a Sesame kind of program or a different level?
Program, but any program that you want to talk about.
Well, I think that my first S, the spine, like everything focuses around an engineering design problem or a investigation, science investigation. Mm-hmm. I think that's like not that subtle, and I think it's way more important than I think we've realized before. So like I think we do units and we design units and we do research on units that are give kids first-hand lab experiences. I mean, I know they're much better than that. But I don't think we really think about sort of the systemic learning around these big ideas and really immersing yourself in one big problem or one big investigation over weeks or months to really get at the complex kind of thinking, like the whole biodiversity topic discussion that we just had. You can't get to that in 2 weeks or 4 weeks. You know, you have to really have enough time that the kids can be grappling with that complexity. And so I think that's something that I've learned in my own research and all these projects that seems to make a sort of fundamental difference.
So you think that we should have more courses where students are really building those kind of activities and evaluating them in some sense? Yeah.
So I think that'd be really cool. We have this model that we use where we create a curriculum story. And again, it's just a template for what the lessons are, what the big activities are, how they all systematically build to the big complex idea. And I think that might be a really interesting instructional activity for a course, is like thinking about mapping out a curriculum story that would have, that would build, to kids being able to design solutions around a grand challenge.
That's great. Thank you.
Yes.
Something that you just said, this is more of a comment, just reminded me of some, it was more anecdotal, about teachers who create these kind of like little stores or economies in their classrooms.
Yeah.
And it's also often related to the community. So there will be like a baker and somebody runs the grocery store and somebody runs these. And so they're learning about money and how to budget and all these other like math concepts and also social concepts. And then, but they're also like going out in the community and going to the grocery store and talking to the people who work there and things like that. And it's like that same kind of thing of contextualizing it and giving it bigger meaning.
Right. I mean, there's got to be just tons of great math there, right? In those contexts. And again, if the kids are going out and talking to shopkeepers or whatever, that's giving them that relevance and meaning piece that, that like their learning has value. I think that that piece also is really important and maybe underemphasized in some of the other curriculum programs that I've seen.
This is more of a question, is I think sometimes the communication between science and math learning gets a little broken up because you need math a lot of times to do science, especially statistics. And so I think that I just want to know if you have any experiences using this to contextualize and give meaning to math learning, as opposed to just like dry abstract math learning that you can do versus. So
we haven't done that as well as I would like to say we've done that better. I mean, I definitely know exactly what you're talking about, and it's. I think the M in STEM is like way under, done. I mean, like we all should be doing more M in STEM. I don't know. But the good news is these guys, the Egypt people, they're like way into really interesting mathematics and applications of mathematics, and they understand the essential math. So I don't know. Like I think that high school in these particular capstone projects I've seen, it seems a little easier maybe to make it more visible and relevant. But that's not really a very good excuse for why we're not doing it more in like middle school. I think it's a really good point. Yeah.
I hesitate to ask this, but what's happened in Detroit after you left? Like I noticed there was 2012, 2013.
Yeah.
Maybe some of your colleagues retired and maybe they're not doing the program.
So what was cool about Detroit is Joe Kraychuk and his team were doing 7th and 8th grade, and we were doing 6th grade, and we were working with a lot of the same teachers, and we were actually sharing and working together on professional development and that kind of stuff. So he left like right before I left, and so after the combination of both people that left that had a lot of NSF grants there, it has the relationship between Detroit and at least that, the science faculty at U of M has diminished. Also, they have a lot of politics going on, and it's been super complicated. But there was politics when we were there, and you just work with the politics. So that piece isn't new. So I don't know enough about their test scores because I'm not immersed in it. But we had fabulous teachers, and we had the superintendent for a while who was a former teacher with us. She was just really good. So for a while after I left, like right after, she was actually carrying on a fair amount of some of the work that Joe Kraychuk's team and our team had done. But after that, I don't know, because she's now gone in that role. And, I don't know, like these are not easy programs to sustain. So if there isn't a real champion, it's hard to know how well it might continue. Yeah.
But it sounds like something like what you did with the teachers in Delaware is something that's sustainable. So
Absolutely.
So not just a program, but really like using the program maybe as an example,
Yeah.
but then that they can transfer that to other units that they
I
teach.
completely agree, because they were like team leaders, and part of their charge was after they did all this stuff with us, they were going out to their buildings and doing the same kinds of, you know, workshops with their own people in their own buildings. So that is a model that I do think will sustain, especially if the state really did adopt the models of the classroom assessment for their state exams, and they seemed like they were definitely doing that. I haven't gone back, I don't have access to their state tests, but those are the kind of things that would keep the classroom practices also going in that way, because again, that's the big, you know, the big metric that a lot of people are still teaching towards is the state test.
So cultivating teacher leaders could be a really key element of the sustain.
Yeah, it's a good point. I have to moderate that S7 a little. Build that in. It's a really good point.
And aligning state assessments with
Yes.
these learning goals.
I have that in a more wordy version of this, but yes, because getting, I mean, and that's why I like that assessment report that specifically calls them out and says, you state people need to be modeling your assessment after what's going on in the classroom. And it's exactly right. I mean, that's where all the rich information is available already. All right. Anything else?
Thank you.
Thank you very much.